Electrochemical cells are essentially cells which generate electric current due to certain spontaneous redox reaction. In this, one fellow is likely to lose electrons. For example, if you take a zinc rod immersed in zinc sulfate solution, connect it to a copper rod immersed in copper sulfate solution, aqueous. And if you connect these two fellows using a bulb, of course, and immediately you can see that the bulb glows. And within 1/100th of a second, the bulb will turn off. Again, if you are connecting these two with something called salt bridge, the bulb continuously glows. You will be wondering why it is like this. It is so because the zinc which is there on the left hand side has a tendency to lose electrons. So as zinc is losing electrons, electrons will be leaving through the circuit and the zinc will be entering into the solution. Now when the electrons are going like this, here on the right side, the solution which has copper plus 2 ions, which are there on the right side electrode solution, they have a tendency to gain electrons to become a red color copper that gets deposited over here. Notice that here in the solution the copper ions are becoming copper atoms, on the left side zinc atoms are becoming zinc ions. Soon what happens in the solution, the zinc ion concentration, positive ions will become more. Here the positive ions will become less. It means here the solution has more sulfate ions, here the solution has more zinc ions. The extra zinc ions would not allow the electrons to flow, therefore flow of current stops. Now if you are using a U-shaped glass tube filled with something like potassium chloride solution, potassium nitrate solution, in an inverted U-shaped glass tube which is plugged with agar-agar gel, the excess of ions travel, therefore the excess of zinc ions will go away, here excess of sulfate ions will go away, electrical neutrality is maintained, therefore the salt bridge will ensure smooth flow of electrons from the left side electrode to right side electrode. The cell works continuously. So this is what everybody knows. Now our problem is how to know whether this zinc electrode, zinc immersed in zinc sulfate, has a tendency to lose electron, and that these copper ions which are in contact with copper metal has a tendency to gain electrons. This ability of different systems to gain or lose electrons is measured connecting them to She. You know what is She? She is standard hydrogen electrode, which is made by taking a glass tube with the opening into which a platinum wire and a platinum block are immersed, and this fellow is kept in 1 molar H plus ion solution, maybe HCl solution. It is continuously fed with hydrogen gas at 1 atmosphere. Now what happens is, this hydrogen has a possibility of losing 2 electrons and becoming H plus ions, or the other possibility is the H plus ions may gain 2 electrons to become H2 gas when connected to other electrode. Here if you are connecting to the other electrode, for example, the other electrode, suppose if it is something like copper plus 2 ion solution, which is in contact with the copper metal. The copper ions have relatively more ability to gain electrons, so they take away electrons from hydrogen and electrons will flow like this. Of course, it also requires a salt bridge. It means relative to this hydrogen electrode, which is maintained at 298 K and in a solution of 1 molar H plus, when hydrogen gas is bubbled at 1 atmosphere, to this hydrogen electrode, relative to this copper plus ions have ability to gain electrons, so it is said to have positive electrode potential. And this can be measured using a voltmeter that is connected parallel to the circuit. Electrons are flowing from, in this case, hydrogen electrode to copper electrode. The loser is called anode and the gainer of electrons is cathode. And now this anode will have minus sign as electrons are traveling through it, and this gets some positive sign as the copper plus 2 keeps on siphoning the electrons out. Therefore, it has a positive charge. It is indicated by plus, it is indicated by minus. The electrons are flowing from anode to cathode. Conventional current flows from cathode to anode. That is opposite to the direction of flow of electrons. We know that. So if I am connecting the same very hydrogen electrode to a zinc electrode, now the zinc rod has a tendency to lose electrons. Here zinc will enter into solution as Zn plus 2, releasing 2 electrons. Here in the solution, H plus ions gain those electrons to become H2. Of course, you require a salt bridge. Notice, therefore, zinc electrode has a potential which is measured by your voltmeter equal to minus 0.76 volts. So all these fellows which have negative potential have a tendency to lose electrons to hydrogen electrode, and those which have positive potential have a tendency to gain electrons from hydrogen electrode. Instead of your hydrogen electrode, which is represented as PtH2 slash H plus. Here it is 1 atmosphere, here it is 1 molar. When this is connected to copper electrode, it can be represented like this. Ladies and gentlemen, now instead of these are single electrodes. Here copper is a single electrode that is connected to sheet. Similarly, you can connect zinc electrode salt bridge to H plus slash H2 comma Pt. It is your zinc electrode. If you really connect copper electrode and zinc electrode, with respect to your hydrogen, it has a potential of 0.34 volts. With respect to hydrogen, this has a potential of minus 0.76 volts. When these two are directly combined, zinc, which is in contact with zinc plus 2 ions, salt bridge, copper plus 2, aqueous solution, aqueous 1 molar, which is in contact with copper. This particular cell has a potential equal to, under standard conditions, equal to the electrode potential of right electrode plus 0.34 volts minus electrode potential of left one minus 0.76 volts. This is equal to 1.1 volts is the useful energy we can obtain. This is called electromotive force. Now, this is the way the cells get operated. Now, let us look at a little other aspect of this. The other aspect which we need to look at is, well, if you are considering a reaction A gives rise to B, for example, it can be zinc losing electrons to give Zn plus 2 electrons. Or it can be copper plus 2 gaining 2 electrons to become copper, whatever. If you consider a reaction A gives rise to B, in this reaction, the energy change in the process is given by delta H. If delta H, heat energy release is there, it is said to be delta H negative. It means it is an exothermic reaction. If the enthalpy or energy change is something that is energy absorbed, then it is delta H is said to be positive. So generally delta H, which is called enthalpy change, during the reaction, if it is released, it is called exothermic. If the energy is absorbed, it is called endothermic. And whenever a process is happening, if along with the A becoming B, B is also becoming A, and if the speed with which A is becoming B is equal to speed with which B is becoming A, then that reaction is said to be in equilibrium state. If it is going in only one direction, it is an irreversible reaction. Reaction can be irreversible, it can be reversible, it can be in equilibrium state. The delta H is the enthalpy change in the course of a reaction. Now, if a lot of energy, delta H is the actual energy released in the reaction. If delta H is the energy released in a reaction. When you are burning petrol, the energy is released which you can use. The heat energy released when petrol is burned, when any fuel is burned, you can use it, right? But can you really use all the energy released when petrol is burning in your car? No. Only a small part of energy is used. The amount of energy that is actually useful is indicated by delta G. Delta G is equal to total amount of energy released minus the part of energy that is wasted. The wasted energy is indicated by T delta S, where delta S is called entropy change. It means some energy is wasted in increasing disorder in the surrounding. The part of the energy that is wasted is represented by T delta S. The part of energy that is really useful to us is given by delta G. The delta H indicates the energy change or enthalpy change in a reaction. Now, thermodynamics has shown that delta G, the useful part of the energy under standard condition, is equal to minus of NFE0, where E0 is called standard cell potential. In our previous cell, it is equal to 1.1 volts, and F is called the Faraday 96,500 coulombs or charge of 1 mole of electrons. N is the number of moles of electrons involved per mole of the substance reacting. For example, when Zn is losing Zn 2 electrons to give Zn plus 2, N value is 2. When Al plus 3 is gaining 3 electrons in another reaction, the N value is 3. So N is number of electrons involved in the cell reaction. Similarly, if you are not using standard condition of temperature 298 K and standard pressure of 1 atmosphere, if you are not maintaining 1 molar solution in the electrodes, then delta G is given by, delta G is overall useful energy obtained, is given by minus NFE. Here, this is cell potential under different conditions. Here E0 means you have taken 1 molar solution of ions in the left side, right side electrodes, temperature 298 K. Here you have not kept 1 molar, something different concentration, temperature is also different. So this is the relation. Sir, we already stated that delta G is the useful part of the energy. Delta H is the total energy released in a process. Therefore, if you want to know efficiency of a cell, efficiency means what is the useful part released out of the total energy released in a reaction. So this we already stated, delta G is equal to minus NFE. So minus NFE by delta H gives you the efficiency of a particular cell. You know the meaning of all the terms. Now, what is the relation between the cell potential under standard condition and what is the standard cell potential? The cell under a different condition of temperature, pressure, under a different condition of concentration is having a potential E cell that is related to standard cell by a reaction E is equal to E0 minus 2.303 RT by NF into log of product ion concentration by reactant ion concentration. This is called a Nernst equation. In this equation, you should clearly understand that, let's take an example. For example, if you are taking this cell, zinc gives Zn plus 2, salt bridge, copper plus 2 copper in this cell. And if you take it 0.1 molar, if you take 0.01 molar, zinc in the course of reaction is combining with copper plus 2 to give you zinc plus 2 and copper. So it means these are the reactant ions, these are the product ions. Always the reactant ions are there in the right hand electrode, product ions are there in the left hand electrode. Now in this case, E cell is equal to, according to Nernst equation, standard cell potential minus of 2.303 RT by 2 into F, here N is equal to 2 because 2 electrons are involved, to log of product ion concentration by reactant ion concentration. If I simplify this value, it works out to be E cell is equal to E0 minus of 0.059 by N, that is 2 into log Zn plus 2 by Cu plus 2. Notice that, in other words, E cell is equal to standard cell potential minus of 0.059 by 2 into log K, because this product ion concentration by reactant ion concentration is called equilibrium constant. So if you know E0 cell value, E cell value, you can calculate equilibrium constant. Or if you know equilibrium constant and standard cell potential, you can calculate the cell potential under given condition. That's all in this lecture. Thank you.